In the name of Almighty God, I'm Master Sankoshi, and today I want to talk about surface species in chemical reaction engineering module in Compton multiphysics simulation software. Surface species correspond to a species bound to the solid interface within the porous pellet, which is also in contact with the pore fluid. The surface species hence only exist within the pellet. The surface species are assumed to be immobile and the concentration is only dependent on the reaction rate of surface reactions involving the species. The derivative of concentration pellet based on the time is equal to R pellet to the power of S. It can be noted that there is no mass flux of surface species between the pellet or across the pellet outer surface and the bulk fluid. The unit of surface species concentration C pellet is amount per area and the corresponding surface reaction rate unit is amount per area and time. When surface species are present, the equation governing transport of bulk species inside each pellet is epsilon pellet. Derivative of concentration of pellet species I based on the time plus R divided by r to the power of 2 and radius of pellets to the power of 2 multiplied by delta minus radius to the power of 2 d pellet I delta p c p I is equal to r pellet for species I plus s b reactant r pellet to the power of s. The second term on the right hand side represents a species production or removal due to surface reactions in the pellet. It is composed of the reactive surface area as a bioreactant, the area per volume available for the surface reactions, and the surface reaction rate R pellet to the power of S. It should be noted that the surface reaction rate for a bulk species R pellet to the power of S and the surface reaction rate for a surface species R pellet to the power of S are related but not identical since the species may represent different molecules. Now I want to go through the non-spherical particles. For non-spherical pellets of any shapes, the relations above can be applied approximately by reinterpreting the pellet radius R pellet as R pellet is equal to 3 multiplied by V pellet divided by R pellet. For reference 18 says where VAPE and I pellet are the volume and external surface respectively of a single pellet of any shape. Since the specific surface is a pellet based on the SI is square meter per cubic meter of one pellet is defined as S pellet is equal to I or area of pellet divided by V of pellet is followed by insertion of equation 3-64 that S pellet is equal to 3 divided by R pellet. For a packed bed of which the packing has a porosity epsilon b, the specific surface of the bed will be SAB is equal to S pellet multiplied by 1 minus epsilon b is equal to area of pellet divided by volume of pellet multiplied by minus epsilon b, or SAB is equal to 3 divided by radius pellet multiplied by 1 minus epsilon b for any pellet shape. Now radius of pellet and SAP can be calculated for any shape and inserted in equation 3-51 and equation 3-57. Some common and specific shapes have automatic support. Now I want to go through the cylinders. For cylindrical shapes, apply equation 3-64 gives R pellet is equal to 3 multiplied by a volume of pellet divided by area of pellet and so on. It is common practice to assume that the top and bottom surface of cylindrical pellets have negligible effect on the mass transfer to and from the internals of the pellet, or R radius of cylindrical is very less than the length of the cylindrical. Equation 3-66 then simplify to R pellet is equal to 3 divided by 2 radius of cylindrical. The equation 3-65 to shows SAB is equal to 2 divided by R or radius of cylinder multiplied by 1 minus epsilon b flex shape. The derivation for a disc-shaped catalyst pellet is exactly the same as for cylindrical pellets, except that the assumption is reversed about the end surfaces and envelope surface. R fillet is much more greater than W fillet, where W fillet is the thickness of the disc. This gives that radius of pellet is equal to 3 divided by 2 W fillet, and SAP is equal to 2 divided by W fillet multiplied by 1 minus epsilon B. Now I want to go to the surface reactions. Surface reactions can also be simulated inside the pellet. Surface species are introduced to pellet by adding them in surface species section of the pellets node available on the packed bed. A bulk species can take part in both volumetric and surface reactions. The total reaction rate for a bulk species within a pellet is defined as R equal to R pellet plus R pellet S multiplied by S B reactant. Here R pellet is the reaction rate for bulk reactions according inside the pellet, and RPAS and SAB are the reaction rate and the reactive specific surface area for a surface reaction occurring inside the pellet or on the interface between the solid matrix and the fluid. Now I want to go to the heat source. The heat source of endothermic or exothermic reactions inside the pellet needs to be accounted for, and the in heat transfer on the bulk level if the heat balance is not solved within the pellet. Thermal equilibrium is assumed in each pellet and source is averaged across the pellet. Q bed is equal to the integral and the lower boundary is V Q a pellet, the derivative of V divided by V pellet multiplied by 1 minus epsilon B based on the SI unit is watt per cubic meter if there are multiple pellet sizes I in the bed. The heat source computed by assuming all sizes cubed is equal to sigma, the lower boundary is I cubed I multiplied by theta bi. Here theta bi is the volume fraction of pellet I in the pellet mix. Now I want to go to the pellet shrinking core. Species diffuse from packed bed through porous reacted shell layer onto the pellet core surface where they take part in the heterogeneous reactions with the solid species inside pellet core are consumed in the reactions, and the unreacted core is shrinking, and at the same time the reaction products diffuse through the reacted layer back into the packed bed. So figure 3-7 illustrates a schematic showing shrinking core model. You see that in the left side we have a pellet with shrinking core, porous reacted layer and thin diffusion layer, and the right section we have a pellet which is equal to the equation R is equal to RC plus S multiplied by R pellet minus RC lamp, and you see that diffusion reaction of a species in porous reacted shell layer solved in extra dimension. The core-shrinking rate depends on the heterogeneous reaction rate and the properties of pellet. Derivative of RC based on the time is equal to R solid MS solid divided by rho a pellet. RC is a pellet core reduced based on the meter. R solid is the surface reaction rate, a molar per square meter second for solid species. M solid is a solid species molar mass. Rho a pellet is the pellet core density. If there are two or more species, the term R-solid M-solid is mass-weighted, assuming same consuming pace is held along the R direction for all solid species. The transfer and reaction equations inside the porous reacted shell layer are solved on a normalized dimensionless extra dimension S between the 0 and 1, which is based on the thickness R of the reacted layer. The general form of the mass transfer equation inside reacted layer is the derivative of concentration based on the time is equal to delta multiplied by d with delta C plus R. The shell mole balance across the spherical shell at radius R where the R is equal and between the RC and R pellet, and we have an integral. The lower boundary is RC and the upper boundary we have R pellet 4 PR 2 multiplied by r to the power of 2, derivative of concentration based on the time dr is equal to the integral, the lower boundary is rc, the upper boundary is r pellet, derivative of 4p r to the power of 2 based on the radius d, derivative of concentration based on the radius dr, plus the integral, the lower boundary is rc and the upper boundary is r pellet 4 p r to the power of 2 RDR. And weak form, we have a integral, lower boundary is RC, upper boundary is RP, let 4P R to the power of 2 minus derivative of concentration based on the times multiplied by supreme minus D, derivative of concentration based on the radius, derivative of supreme based on the radius plus R supreme is equal to 0, defining extra dimensional coordinates S as S is equal to R minus RC divided by R pellet minus RC. The integration can be written as the integral, the lower boundary is RC, the upper boundary is RP, and so on. There R is equal to the integral, lower boundary is 0, and upper boundary we have a 1, and so on. The derivative of radius based on the S ds for time derivative in moving coordinate system. C time is equal to ct plus derivative of concentration based on the x time. On the extra dimensions, the mass transport equation to be solved inside the reacted layer is formed from equation 3 68, 69, and 70. 4p and a pellet r to the power of 2 multiplied by minus epsilon pr multiplied by r time minus derivative of concentration based on the time, and r time is multiplied by separate minus d derivative of concentration r and derivative of supreme based on their concentration plus R supreme dr divided by ds is equal to 0, where epsilon pr is the porosity inside the reactive pellet for the pellet shapes, diffusion process, and heat sources. They are similar to that for post-catalyst pellet. The shape can be both spherical and non-spherical particles, and the characteristics and properties of the pellet are defined the pellets not under the porous material. The heat sources are contributed from the bulk reactions and shrinking core reactions for surface reactions. Now I want to go through the shrinking core reactions. The pellet core consuming rate depends on the rate of shrinking core reactions. Equation 3-67. The solid species in the pellet core take part in the heterogeneous reactions as reactant. The pellet core is shrinking with the proceeding of the surface reactions. If there are two or more solid species, and shrinking rate is the mass weighted consuming rate. And here it is supposed that all solid species shrinks at the same pace along the radial direction. Boundary condition outer surface. There are two types of boundary conditions on interface between the pellet outer surface and the fluid in the bed. Continuous concentration and film resistance and mass flux, they are the same as that for catalyst pellets. Core surface. The core consuming reactions always exist on the core surface. Besides the solid species in the pellet core, there could be also bulk transport species that participate in the heterogeneous reactions. The surface reaction rate for the bulk species is a kind of the mass flux J pellet I between the core surface and the porous reacted layer. The mass source of the species C pellet I is equal to R pellet I is equal to S area multiplied by J pellet I plus C pellet I epsilon PR and dr divided by d time, where SA area is equal to 4p RC to the power of 2. And articles and literature that I read was written, the sources and references by the Codina, and the name was a discontinuity capturing cross-bond dissipation for the finite element solution of the convection diffusion equation. Another one was written by Danckwerts. The name is continuous flow systems distribution of residence times, and another one was Millington and Crick, and the name was permeability of porous solid. So thank you so much, and we have so on. It's about 80 references. Thank you so much for watching my tutorial video until the end. Today is 19th of May 2026. Time is 9:58 a.m. Also, you can download the appropriate and prepare uh, proper consult file from my github.com/masters.